A probability space has three elements: the sample space, omega, a sigma algebra defined on the sample space, f, and a function that we will define now that we will call a probability. A probability is a function defined from the sigma field f to the set of real numbers between 0 and 1, such that probabilities are always positive and between 0 and 1, such that first, the probability of the sample space is 1. Okay, so this is like a normalization. And 2, if the set A sub I is in F, and A sub j is in F, such that AI and AJ are disjoints, then the probability of AI union AJ is equal to P of AI plus P of AJ. In general, if we have an infinite sequence of sets in F, so in general, if we have a sequence of sets that are disjoint, AI intersection AJ is empty for all IJ, then the probability of the infinite union is the sum of probabilities. Okay, so these are known as the axioms of probability. Okay, when we define probability as a function from 0 to 1, these two axioms are sufficient. Or if you define probability as a real valued function, then you would add a third axiom, and that would be that probabilities are non-negative. Okay, so as a consequence of these axioms, the following properties just follow really easily. For example, the probability of the empty set is 0. Why? Because the empty set is nothing but the empty set union omega, and the probability of empty set union omega is equal to, by definition, empty set union omega is omega, so that's 1. But by the additivity axiom, which is axiom 2, this must be equal to the probability of the empty set plus the probability of omega, but that is 1. So from this it follows that the probability of the empty set must be 0. What else? Now, similarly, it follows that the probability of the complement of a set is 1 minus the probability of the set itself, right? And it follows in exactly the same way that we showed the first one. Okay, so now let's say, before we explore further properties, let's give an example of a probability space. For example, our sample space is the set ABC with 3 elements. Okay, and construct a sample space F1. I'm sorry, the algebra F1 as empty set omega A and BC. Now, in order to characterize a probability law for this set of events, Okay, all we need to do is specify the probabilities of the elements of the sigma field, or in this case a field, or I use sigma field interchangeably with sigma algebra, and field interchangeably with algebra. So this is an algebra because the underlying sample space is finite. So all we need to do in terms of the description of our probability law, we need to designate the probabilities of the elements of F1. For example, these could be 0, 1. Well, these have to be like this, right? And for this, we can use 0.55, say. And for this, we can then use 0.45, so that the union will have a probability equal to 1. But note that in this case, we do not need a detailed description of the probability law to specify for us the probabilities of individual outcomes, because apparently our field does not contain all individual outcomes, so that is not the level of detail that we're interested in. However, if we had the following field or algebra, F2, which contained more detail, in fact, suppose it contained A, B, BC, and AC, and C, and AB, then we would have, let's say, 0, 1, and then assign a probability to A, and this would be PB, this is PA, this is PB, and this would be what? Well, once we define PA, the probability of this set BC is automatically determined as 1 minus PA, clearly. And then this is determined as 1 minus PB. This is determined as 1 minus PA minus PB, and this is determined as PA plus PB. Okay, so as long as we obey the rules, which are the axioms, everything in probability theory will be following. Everything else will be clearly defined. For example, we will have the property that probabilities are monotone. Let's prove that. So if, let's see, let's call it monotonicity. If A is a subset of B, then PA is less than or equal to PB. Why is that? Well, now if A is a subset of B, then B can be written as A union the difference of B from A, which is non-empty. Okay, then by continuity of probability, I'm sorry, by additivity of the probability, since these two sets are by definition, by construction, disjoint, P of A plus P of B difference A, and then clearly the result follows from here. Okay, so from the axioms, we can define everything else in probability that will follow in this course. Let's now look at a continuous probability law. For example, let's define the uniform probability law. Okay, a uniform probability law on the interval from A to B. where A and B are in real numbers. Okay, in this case, our sigma algebra will be the Borel sets on A to B. And our probability law would be the probability of an interval will be the size of the interval divided by B minus A. Okay? So that would be the uniform probability law on a piece of the real line, which is a continuous sample space. All right. Now, there are a number of other properties that you can easily define, you can easily prove, starting from the axioms. Now I will introduce something that is closely related to the definition of probability, which is conditional probability. Conditional probability. The conditional probability, suppose we have events A and B from the same probability space. Okay, obviously then they come from the same sigma algebra. The conditional probability of A given B is defined as the probability of A intersection B divided by the probability of B whenever the probability of B is not 0. Okay, if the probability of B is 0, we cannot define a conditional probability based, conditional probability conditioned on B. Now, conditional probability is a legitimate probability law, and we can go and show that it satisfies the axioms of probability. I would strongly urge you to do this as exercise. Okay. Now, what are some immediate corollaries of this definition? Let's see, corollaries. First of all, the probability of A intersection B can be computed as the probability of B given A times the probability of A. Well, that simply follows from noticing that P A given B times P B is equal to P A intersection B from definition, and this follows in the same way. Okay. Well, secondly, the probability, well, as an extension to this, A1 intersection A2 intersection AN. So the probability of an intersection of a bunch of events, like a chain rule, can be found by multiplying the probability of the first one, or one of them, an arbitrary one of them, multiply the probability by the probability of another one conditioned on the first one, multiplied by the probability of the third one conditioned on the first two, and so on. And the multiplication would go until the probability of the last one conditioned on all the previous ones. Okay? And this trivially follows from the first corollary that we showed. Okay. So now an important thing is the total probability theorem. Let a sequence of sets Bi be all defined on the sigma algebra F. Okay, say I from 1 to n. Okay, such that these sets are all disjoints. Okay. Then if they have non-zero probability, okay, bigger than 0 for all I, and if the probability of their union is 1, then we can use these sets Bi as a partition based on which we will divide and conquer the probability of any given event. So for any given events in our sigma algebra, the probability of the event can be written in terms of the probability of this event conditioned on the Bi's. Okay? Of course, we do not need an infinite number of Bi's, but total probability theorem holds in the infinite case as well. We can, for example, have B1 and B2 would be B1 complement. And we can then write P of A as probability A given B, PB, plus probability A given B complement, probability B complement, and that would be fine. And that is something we do a lot of the time, actually.